Hi. Hi. Okay. Hello. 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 Okay. Hang on. Bear with me for one. Hello. All right. Bear with me for 1 second. I'm totally fakakata here, which means exactly what it sounds like it means. Hang on 1 second. Hold on. I'm so sorry. I'm trying to. Sorry. Okay. More people coming. Sorry. So confusing. Okay. I've been suffering a lot of technical issues. So, hi, Hannah. Hello, Fahima. Hello, Yulia. Hello, Almadina. Good afternoon, Noreen. Hello, Kareem. Hello, Kazi. I'm very fine, thank you. How are you? I don't mean I'm very fine. I mean I'm fine, thank you. Hello, Shasha. Hello, Adriana. Hi, Cassandra. Hello, Kwan. Hello. Yes, I hope everybody's doing well too. That's so nice of you to say that, Alex. Yes. Let's all hope that Alex is right, that everybody's doing well. Hi, Rachel. Hello, Anna. Oh, I think I'm going to be getting a direct chat on that one, or I should be. Please correct me. So hello, everybody. Sorry we started late today because of the whole rotation thingy do thing. And thank you for your understanding as always. Once again, I want to say I owe you a bunch of videos or a really long video. I'm aware of that. It's on me. It's not on you. This semester is one of those things that's starting to pile up, but I owe you video or much video or something, and it hasn't happened yet, so there's nothing that you should have or could have done. Hold on, I'm just changing the screen. Oh, let me also say the reverse. Hello, Cassandra. Hello, Kazi. Hello, Shasha. Hello, Kareem. Hello, Fahima. Hello, Yulia. Hello, Rachel. Hello, Grisella. I didn't say hello, Grisella. Hello, Kwan. Hello, Elena. I don't think I'd said that. Hello, Anna. Hello, Noreen. That's a hello to everybody who doesn't have a black box. Okay, so we have the short class today, so we're going to get rolling with it like now. It's on. Oh, it's not on that. Oh, sorry. Oh, in fact, oh my gosh, everything is discombobulated. Hold on, now you have to watch how the sausage is made. Pardon me for a second. Quick announcement while this Mishigas is happening. normally this is a rotation and all of that. Like normally this would mean that next week you would have the full 2.5 hours, but unfortunately, I think that's not going to happen. Just as a distant early warning that next week we're probably going to meet again at 4:30 instead of 3:05. I will again send out an email confirming that and all that and give you the points, which you're all very good about. I appreciate. But just as a warning to your schedule, we're probably doing this half class thing 2 weeks in a row because in Physics 203, they have an exam next week. We don't have an exam here yet. Don't worry about it yet. But so that's just a warning that we might have, and so I might owe you even more time. But that's the reality of that. Pardon me for a second. So confusing. Pardon me for a second. I know this is all happening live, whatever that means. The other classwork. Say my apologies. This is not what I want to be spending your time on right now. This is pardon me for a second. Okay. Okay. This is where we are. All right. So what I would like to begin discussing with you today, if you will indulge me, but I would like to begin discussing with you today is a thing called the Doppler effect. I'm going to get your feedback for a moment, and it involves the equations that are, so this page is for you, this thing sitting here. I expect that most of what's on the page looks like gibberish, perhaps. My goal for today is to break down what's on the board and make it not gibberish, as usual, I guess. I want to just make sure that I'm not crazy, though. Let me just check in with you guys on a couple of things. Here's what I think. I think I would like to discuss the Doppler effect. It's something you need to know. I think, number one, I'd like confirmation you have not heard of or discussed or encountered the dot. You have correct. Is this, oh my God, I can't speak. Is it correct? Nice. Wait, that's good. Thank you, Leah. That is what I'm writing there. Now, okay, you might have just saved me a moment. Oh, wait. Oh, okay, thank you. You're saving me from myself. That is kind of what I was going to ask. Okay, cool. So you did, all right. So you did that equation in lab. Good. That's what I was kind of hoping. That's good. But is it correct? So I'm asking Yulia and Noreen and everybody. You guys are saying the equation V equals lambda F you've done in lab. That's great. That helps me a lot. but you're not heard of the effect in lab. Okay, thank you, Hannah. You guys are like good listeners. I don't know how you do this. All right, perfect. That's what I was hoping. All right, so to say to everybody else who's not quite as good at human engagement as these four are, anybody else who's like me who can't follow their way out of a paper bag. So the assumption of today is that you have some knowledge of waves, that you've been seeing some things about waves, both in lab and in lecture last week with me, that you have some understanding of waves, in fact, including an understanding that for any given wave, V equals lambda F. I'm going to review that for a moment in a moment. But you have not seen that applied yet to this thing called the Doppler effect. That's what those four people in the room seem to be confirming. And that's what so today's goal is to take what we know about waves. Oh, thank you. Did I not? There should be. Sorry. Oh, thank you. No, there should be. That would be my bad. Thank you. I'll do that right now. You're so responsible. This class is so responsible. I wish you guys were. I don't know what I wish. I was gonna say I wish you were my family. That's a little weird. But you are very responsible. All right, hold on. I'll put the game thing in right now before I forget. But thank you for being so on top of things. Hold on a second. This is what the problem with me teaching two classes at the same time is that it's like teaching two classes at the same time. It doesn't work. Right, hold on. I could have sworn I did this. I'm really losing my mind. Okay. I really didn't do this? No, I guess I didn't. I guess you're right. Okay. Okay. Thank you for that, Hannah and others. Okay, so the game turn thing is now there, or I think you should see it in a moment. I think you'll confirm. All right, my goal is to take what I believe you know about waves already and to supplement that with what I would claim is universally true about velocities. So I'm going to review briefly. We're going to remind ourselves of something that's true about velocities in general. And that's the equation that's written at the top of this page here. Okay. The VAC equals VAB plus VBC. That is something that I'm not saying you've necessarily seen it written that way before in this class. Maybe you saw it written that way in Physics 101, maybe depending on where you took Physics 101 or with whom. It is a thing, but even if you've never seen it before, I'm going to explain it in a minute. It's just a certain way of writing a concept that you definitely know. And it's a concept that has to do with how velocities work in general. Okay. Then underneath that, what you see on the page is you see a couple of different versions or different subscripted versions of V equals lambda F, which is a very specific statement about velocity of a wave. We're going to put those two things together and get this thing called a Doppler effect. Okay. Okay. So Oh, sorry. The word in the, good question. Uh, the word in the quotation is Doppler, Doppler. Sorry, that's not really what. Okay, so we're going to discuss this thing called the Doppler effect. I mean, many of you have heard of it, or you've heard of like Doppler radar and in weather reports and things like that, or Doppler radio or something. And maybe you've literally specifically heard of the Doppler effect. I will tell you to cut to the, so there's a lot that I do want to say about the Doppler effect. There's math involved in the Doppler effect. There are a lot of really, I think, important implications of the Doppler effect that show us something about motion. It shows us about wave motion. It shows us about the motion of the universe ultimately. But it's also a very common phenomenon. So before I get into all the details and all the math and all the concepts, let me just say that the short version of the Doppler effect is, that's the Doppler effect. Like, put more specifically, and again, this is not worth writing down. This is just worth, having in your mind. If ever you've been standing around in New York City and like a motorcycle or a car or a car or an ambulance or something approaches you and then passes you, and if you hear if you're familiar with this phenomenon, this idea that when the vehicle approaches you and then starts going away from you, you hear something funny happen to the sound. You hear something like, Now, honestly, you hear a lot of things, actually. I mean, I want to back up for a second. I mean, I cannot speak. When a sound approaches you, as it gets closer and closer to you, it does get louder and louder. And as sounds get farther and farther away from you, they get lower and lower in volume. Like, that's true about sound waves in general. That's true about sound in general, but that's not actually what I'm talking about here. Like, it certainly is true that the volume of a sound wave is associated with the energy of that sound wave. And as sound waves travel through air, they tend to dissipate and they encounter friction in the air. They encounter resistance, and the amplitudes of those sound waves do tend to dampen out. They do tend to get lower. So the energy of the sound waves do tend to get lower. And so by the time sound waves hit your ear, if they've been traveling for a very far distance, they tend to be lower volume than if they were produced right next to you. I mean, sort of everybody knows that at some intuitive level, and it's totally true. And it's true for all the intuitive reasons you might think, but that's not what I'm talking about here. I want to start by saying everything I'm going to say about the Doppler effect today. The Doppler effect is a phenomenon that occurs with waves in general. Among the more common or more familiar and comprehensible versions of the Doppler effect happens with sound waves, but it can happen with any kind of wave, okay? And what the Doppler effect has everything to do with is the frequency of a wave. So before I go any further, let me say this. Okay, we're going to talk for the rest of at least today and some other. Yeah, very good question, Quan. That is a very good question. Okay, hold on, let me back up for a sec. So just in case people can't read, in the chat, Quan's question says, does a big wavelength mean a louder sound? That is a great question, because in fact, it's like exactly the type of thing that I want to address in like the next 2 minutes, like in this list of brown numbered items that I'm about to put on the page. That's exactly the kind of thing I want to address. Now, to be honest, the answer is no. It's a great, perfect question. And honestly, truly, I want you to submit that for points, and you'll get 11 extra points for the fact that I'm actually going to go out on a limb and say, with all respect and politely, that the answer is actually no, it doesn't. Right. Okay. So to everybody, this is exactly what I want to break down for everybody, but there's no way you would know that unless you knew it. So it's a totally reasonable question. What I want to break down for everybody is the relationship between like the frequency or the wavelength or the amplitude of the sound wave versus how your brain actually interprets it. Like that is part of my goal today in the next minute. Now, the truth is, Julia's hypothesis happens to be more correct. I hate saying that. I mean, but what Julia is saying is actually more the truth than what Quan is hypothesizing. Well, no, Julia was right the first.
Oh, you know what, Professor? You just keep going because I'm going to keep guessing and we're going to take the whole
your
class.
guess is right. Yeah, to both of you, no, you're totally asking the right thing. I'm going to keep going just so I don't get myself all tongue-tied. But yeah. Like I'm going to address that in a minute. Before I even say that, let me say to everybody, what you're learning in lab, and hopefully what you're learning with me in general, with the math and with the demonstrations in lab, you're learning about waves in general. And waves are a type of motion, and anything that you ever say about waves, if it's true about waves in general, then it's true about all waves. Like all this math stuff and all this wavelength concept, frequency concept, true about any kind of wave motion. Now, sound is a really great example of a wave. Like it's very, very real, very familiar, very common. So we're gonna focus our attention on sound waves a lot because it's just such a real important example. So now I have to break down the translation of when we're talking about sound, how does the math and everything apply? First thing I have to say about sound before I even get into volume or amplitude or anything like that, first thing to say about sound is I just have to honestly tell everybody something that's slightly confusing. Every time we draw waves like this, or you look at waves like this in the lab or something, those are all graphs, and waves can look like that. Like if you hold a long string and you shake the string, you can make waves that actually do look like crests and troughs, or even at water waves at the beach do look like they have like bumps and valleys, crests and troughs. Those kind of waves that we talk about on graph paper and in the lab or on a string, those are technically called transverse waves. What transverse means is that the oscillation, and you might want to write this down. I'm not going to write it down because I want to stay the course here, but what transverse actually means is that trans means across. So a transverse wave propagates along an axis that is across, that is perpendicular to the oscillation axis. Like all of the waves that you're studying, either mathematically, theoretically, or actually, like all the ways that you're picturing going across strings, you're picturing situations, and this is how we originally broke it down in lecture 2. You're picturing situations where something oscillates, and something next to it oscillates, and something next to it oscillates. And so then you get this pulse, right? Or this disturbance or whatever that propagates this way. You're picturing everything and it's correct. I'm not saying anybody's doing anything wrong, but everything that we've been like picturing in our minds or easily putting on graph paper, we're picturing situations where the propagation, the traveling of the wave pulse itself is perpendicular to all the little oscillations that cause the wave. That's called transverse. It can happen on a string. It can happen on the surface of ocean water. There's another type of wave, though, that has all the same math, all the same understandings, but is a little bit harder to picture. And this other kind of wave is called compression, or sometimes called longitudinal. And this kind of wave is actually what sound is, just so you know, so we're not lying to you or something. What happens in a compression wave is, again, all the same math, all the same features. You have amplitude, you have frequency, you have wavelength, but in a compression wave, all the little oscillations are actually along the same axis as the propagation. So if we were trying to make a, like if we're all in Yankee Stadium or something and we're all human beings and we're going to do a wave, right? If we're in Yankee Stadium, what people generally do is a transverse wave. Like I go up, then I go down, then the person next to me goes up and then goes down, then the person next. And so you get, every person goes up and down, but the ripple goes across. That's a transverse wave. We're oscillating on this axis, but we're propagating on that axis. That's a transverse wave. If instead you imagine doing this, it would be a little bit harder, but you could do it. If instead of me going up and down, if I went side to side, like I didn't hit the person next to me, but I just went side to side. And then the person next went side to side and then side to side, kind of like taking a long slinky, like a wide slinky and flicking like one end of it. So it goes like that. That's a compression wave. Again, all the same math and stuff, but there in a compression wave, instead of, you still have crests and troughs, but the crests are little pressure pockets. A crest means when all of the little slinky pieces or the little human beings are pressed together and then they spread apart, and that's like a trough. So instead of literally peaks and valleys, you have what we call compressions and rarefactions. I mean, that's the word for rarefactions. Like high pressure pocket, low pressure pocket, high pressure pocket, low pressure pocket. That's called a compression wave. It works just the same as a transverse wave, but it looks different. Another example of a compression wave would be like a seismic wave, like earthquake stuff, like when, or like the Tasmanian devil, go anything like going underground when compressions like move under like the tectonic plates of the earth or something, and you get like earthquake type things when the ground ripples from here to here. What's happening is pressure pockets under the ground are going bum, 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 bum. That's a compression wave, and that is really what sound looks more like. Like I vibrate the air molecules near my tongue, so they get closer together and then they spread apart. And then these air molecules get closer together and then they spread apart. And so air molecules aren't actually going up and down. They're going side to side. Okay, just that's one detail. And that's why when we draw sound waves on pieces of paper, we don't usually draw the squiggly thing. We draw like those ripply, arcs that coming out just to express that fact. Okay, that it's just a detail, but just so that you can picture it better. So sound, first of all, is a compression wave, generally through air at standard temperature and pressure. Now I want to address, and then I want to address the thing that Quan was asking and Yuli says, but does that mean that does that mean there's, no, great question. But what I want to enforce now is, again, perfect question, but actually the answer is no. Everything that you ever believe about all your graphs and everything you believe about frequency it depends what you mean by set, but anything you ever believed about frequency in a transverse wave will still apply to a sound wave, to a compression wave. It's just that what it actually physically looks like is different. So I think we'll see if this helps. Okay, cool. Okay, so sound waves are compression rather than transverse. Then second of all, yeah, I think, I'm gonna look in the chat in a second, hold on. I'm going to look at the chat. I'm going to explain this. Obviously, I saw something happening in the chat. Oh, yeah. I mean, so, yeah, ultrasound. So, right. Like in the medical context, when they talk about ultrasound and stuff, they are talking about, yeah, they are using the word in the correct way. What they really mean by ultrasound is that the frequency of those waves are high. They are like high frequency, even for sound waves. That ultrasound is sound, yes. And by ultra, they mean it's like high frequency sound. So it's such high frequency that you don't really hear it as a sound. It's like a dog whistle almost, but it is ultrasound equipment that you use. But it is, yes, it is still a compression. That's right. It is still a compression wave. Right. Thank you. Good question. Absolutely. So let's talk about this for a second. So yeah, like if I send a compression wave through the air at standard temperature and pressure, what you interpret as high or low, what your brain and your ear together interpret, experience as high and low pitch, like as in note, as in register, like as in on a piano. When you register something as high, what that is literally a high frequency compression wave through the air. When you register something as low, it's low frequency, and literally, like very literally, like numerically, like for any of you in the class who have ever, even for 1 minute, studied a musical instrument, or even just like if you've listened to a lot of music, right? If you could picture a piano, okay, and if you picture a piano and you picture the notes on a piano, I know not everybody knows what I'm talking about here. I apologize, but if you could picture like the white keys on a piano, and many of you know that like they're labeled, like the notes have different names, like C, D, E, F, G, A, B, and then it starts again, C, D, E, F, B. I forgot my alphabet, C, D, E, F, G, A, B, and the black keys in the middle are like sharps and flats, if you know what I'm talking about. And again, if you don't, it's okay. But if you press that middle C on the piano, the C that's in the middle of the piano, you press that, and somebody next to you, either a piano tuner who has like really good pitch, or just a musician person who has a really good sense of pitch, or just even a normal person, if you press that C and they're like, oh yeah, that's right, your piano's in tune, that's good, yeah, it's a middle C, that's good. What they're really saying is, yes, the air, yes, that string that was just hit by the hammer of that key just vibrated at 256 cycles per second. Like, that's not an example, that's literally true. If it's a correct middle C, then that means the string is vibrating at 256 cycles per second, hertz, okay? And then that means that the air molecules were hit by that string, and the air molecules are now vibrating, like going at 256 cycles per second. And then they eventually reached your eardrum, and your eardrum vibrated at 256 cycles per second, if it's a middle C, okay? And then that sent an electric signal through your brain whose electromagnetic frequency was 256 cycles per second, okay? If, for example, it was the middle A on the piano, then it was 440 cycle. And these numbers are real, like very real. Like, this is Western music is tuned to these numbers. If they, and I'll go a little bit further. So a couple of things. First of all, if they hit the right note, and I don't care, like if you listen to music at all, if you have any sense of music, even just the one song that you ever like, right? You know whether it's done correctly or not, right? Any of you who ever listens to music at all and has a song that you like, if someone else tries to sing the song that you like and they blow it, like they hit the wrong note, at a certain point, you know it, right? Like maybe they might get away with a little bit of wrongness that you might not be able to tell. But depending on how musical you are and depending on how musical they are, if they get it wrong enough, you're going to be like, oh, dude, no, that is not how that part goes, right? Say they might hit the note like really flat, like the note's supposed to be up here and then they hit it too down low. Now, you might not know a lot about music. You might not know a lot about math. You might not be doing math, but if they hit the note too low, you know it's wrong, right? What does it mean for it to be wrong? It means the frequency is too low. If that piano is out of tune, if you know there's something wrong with the piano, it means the middle C is not a 256. It means the middle C is something like a 246 or something. And you're like, oh, even if you don't know the numbers, I'm telling you the numbers are what's going into your brain is what I'm trying to say. So if someone hits a correct middle A, what happens is that number 440 actually like vibrates the string, then the air vibrates at that number, then your eardrum vibrates at that number, then electrical signals in your brain vibrate at that number. And that's just that one note. And that translates, a wave has now gone through like 4 different media. It has changed a bunch of aspects of it, like we're going to get into in a minute. Like if the wave has traveled through like 4 different media, and I mean by that, I mean like first it was in a string, then it was in air, then it was in cartilage, then it was an electrical signal. And maybe some of those times it was a compression wave, like when it was going through air. Maybe by the time it got to the electricity in your brain, maybe then it was transverse. If it went through 4 different media, it might have changed its speed 4 times. Like this now going back to your lab with Walters, with the thing we have to get into today with whatever time we have, like every time a wave travels through a different medium, it travels at a different characteristic speed, right? So the speed of that wave might have changed each time. Like when that sound was going through air, it was propagating through the air at 340 meters per second. Then when it was going through the cartilage of your ear, maybe it's a different speed now, etc. So each time the wave changed its speed, therefore, since V equals lambda F, as you know, apparently, right? Since V equals lambda F, if each time it changed to V, it necessarily also changed its lambda, like the wavelength might change each new medium it goes through, but somehow, this is to partially answer Kwan's question and partially answer Yulia's conjecture and so forth. What I'm saying is if someone plays an A on a piano, after this weird signal, this pulse, this bit of numerical information, after it has somehow made an immaterial journey through like at least 4 different media, by the time it gets to your brain, one thing has remained constant throughout. And that's the frequency. For somehow, some way, what continues to happen is a vibration at a rate of 440 cycles per second. If we're playing an A, or if we're playing a C, it would be 256 times per second. Let me be more specific, by the way, especially for those of you who do follow music. If you played, so I'm saying the middle A is 440. If you played an A an octave up, if you know what I mean, if you like, you went up to the next key on the piano that looks like that original key. If you went up 12, right? All right, so I'm gonna look at that for 1 second. But if you went up to the next A, what that is literally a frequency of 880. And that's not an example, that's the truth, right? And I'm gonna look at Kazi's thing in the chat in 1 second. But like, in other words, every one of these notes has a number associated with it. And the reason that some notes sound right together and some don't is that some of the numbers work well together and some don't. What it means to be an octave up is to be an integer multiple up of a certain base frequency. Like the next A up is exactly as you would guess, 1320 hertz, like for real. And all the C's are integer multiples of 256, like they literally, so what's being sent to your brain when that note travels through string, through compressed air molecules, through ear cartilage, through electrical, signals in your brain, what somehow is making that entire journey is the number 440. And if that number is slightly off, if the piano is slightly out of tune, and if instead of sending a middle A, we send something a little bit flat, like a 430, your brain knows it, whether you do the math or not, right? And you're like, oh, that's the wrong note. You're really saying, oh, that's the wrong number. It's really what's being sent when we send a sound note. When we send a sound pitch, what's being sent is a wave frequency, is a very specific number. And if the frequency is different, then the note is different. Let me just pause so I can see what's in the chat. Cause there's something in the chat. Hold on a second. Oh, great. Perfect, Kazi. Yeah. So what I'm ultimately getting at, and if I run out of time today, I apologize, but yeah, what I'm saying is somehow the medium doesn't seem to have an effect on the frequency. The medium through which the sound wave travels will affect the speed and therefore it will affect the wavelength, but it won't affect the frequency. That's right. And I don't know why. I think that's like a crazily interesting thing. Like Kazi's question is exactly right to ask that. Like that's almost confusing. I mean, it is confusing. I mean, I don't know how nature does that. But yeah, thank you. No, that's great. But that's the thing that gets through. And this is one of the reasons that when I think of wave propagation, when I say a wave travels from here to there, like it's not something material. Right. So what is traveling from here to there? I say what's traveling from here to there when we send a wave, what's traveling is information. Like literally what's traveling is a freaking number. I don't get it. I really don't get it any more than Kazi. I mean, I know it's true, but what penetrates through all the mediums somehow, all the media somehow is that frequency number. It remains unchanged throughout the media. And that's why we like can communicate through sound. Like and music and so forth. Like, okay, so yeah, great question. So frequency is pitch. Volume, I'm sorry, amplitude. Let me look at the chat. Yeah, right. Oh, yeah. Oh, great. Okay. There's a lot of, so in Diana's question, there's a lot of good questions going on here in Diana's. First of all, she's totally right. So I don't know if I can, well, I think you can all see it. Wait. Okay, wait. Okay, wait. So there's a lot of good questions happening here. One good thing about these questions, it's clear that you guys do know something about, I mean, apparently we're, oh yeah, you can see it, right? Okay, cool. So look, it's pretty evident from these questions that we are talking about something that people can really relate to in the room, that you guys can relate to and have some different experiences, which is great. So part of me just would totally like to just keep talking about all this for like weeks. And in some ways we will. Like this is where physics becomes very, very, and math become very, very real. And I love music too. And I mean, I think, and yes, it even has medical implications and all that. I'm not going to be able to answer all of these questions perfectly adequately without getting fully off into another zone. I'm going to sort of try, but I appreciate that people are really relating here. I'm going to try to answer these questions, but also bear with me because I'm going to have to sort of do it in a maybe overly linear way. So let me write something and then try to answer Kazi's or Diana. Diana is asking about like 3 different questions at once. I mean, they're all good. And then Kwan is also asking something. Let me see. So bear with me for a second. I mean, I see the questions. Let me first of all just get out of the way one thing, which is this. Okay, first of all, just to get some facts out there, this is not going to fully answer Diana's question or Kazi's yet, but just to get the facts out, like for a sound wave, frequency is pitch, like note, right? And then the square of amplitude, I mean, this gets a little complicated to it. That's why I just want to get it out there. The square of amplitude is what determines energy for any wave, for any kind of wave. And the energy of the wave is ultimately proportional to the square of amplitude. I can't get into a whole discussion of why that is right now. I did want to make a video and a PowerPoint about this that I can post for you if you very much care, but a quick a quick sort of reason as to why it's the square of amplitude is, if you remember, waves are made up of harmonic oscillators. And if you remember, all oscillators are like little springs, masses on springs going up and down, going up and down. And remember, with like a mass on a spring system, this goes all the way back to homework 1, at any given moment, the kinetic energy of a mass on a spring is 1/2 mv squared, and the potential energy of a mass on a spring is 1/2 kx squared. So that's not a proof of anything, but just to remind you, like, energy tends to be associated with the square of positions and speeds in any kind of dynamic system, and that remains true in a wave. However high the wave is shows how high the oscillators are, or how high a peak is, or how tightly packed a bunch of a compression packet of air molecules is. That's an indication of where the molecules are and how fast they're moving. And when you square that, you get an indication or a proportionality to the energy of the wave. This is for waves in general, that the energy of a wave is proportional to the square of the wave's amplitude. And that has a lot of implications. I mean, I have to say, because other things follow from that. But then from energy, we get something called intensity. Like technically power is energy per time, and technically intensity is power per area. I mean, these are all technicalities in a way, but what that ultimately means is, like, for something like a light wave, not to jump ahead, but just to give you perspective, for something like a light wave, frequency is color and amplitude squared gives you brightness. Like, for a light wave, intensity gets translated or interpreted as brightness. That's just as an example. For a sound wave, like we're discussing here, for a sound wave, intensity manifests itself as volume. Okay, so in other words, this square of the amplitude yields energy, which yields intensity for any kind of wave we're talking about at all. In the specific case of a sound wave, the square of amplitude ultimately determines volume. Now, I'm just saying that almost to get it out of the way. I still want to try to go back to Diana's question and Kazi's question and other people's, but just to sort of like lay the groundwork here, then if I make a sound and you hear it, I'm sending compression waves to you. They have mathematical characteristics like frequency, wavelength, speed, amplitude. The speed of the sound wave is going to be determined by medium, the speed. Oh, in fact, let me write that down before we forget. Sorry. This still doesn't answer. I'm going to keep saying this because I feel this still does not answer Diana's question yet, or Kazi's, or anybody. Like, I want to get to theirs, but again, just before I lose my mind, I just want to say, if you're sending sound through a medium of air at standard temperature pressure, then VWM, by which I mean the velocity of the wave relative to the medium, so in this case, relative to air, this goes back to 2 weeks ago now, or to yesterday. Once you specify the medium of a wave, then you have fully determined the constant speed of that wave relative to the medium. So if we're talking about sound going through air at standard temperature and pressure, then sound will travel through that air relative to that air, compared to that air, at approximately 340 meters per second. If you change the air, then you change that speed. If you don't change the air, then that speed doesn't change. The frequency of the sound will determine the pitch of the ear that receives it. The wavelength of the sound won't directly determine anything. The wavelength just gets smaller if the frequency gets bigger, given a certain speed. The wavelength gets carried by the frequency for the ride, but so frequency is pitch, speed is determined by medium, the amplitude squared ultimately determines volume. And so now, so now that's like the overview of how sound works. There's a lot of implications of this that I want to get to with the Doppler effect, but let me see if I can relate this back to the questions now. Hang on a second. Okay, so with Diana's question, Diana's totally right. What she's onto here, and like some of you may be familiar with this, some not. Like Western music is all based around this idea that the middle A. I know you hear about middle C a lot, but Western music, like since Bach, is tuned to is organized around this idea that we tune the middle A to a frequency of 440 hertz. Again, that's not an arbitrary example. That is an actual like thing. What Diana is getting at is that that's a choice that that Western white civilization made like about 400 years ago. It's a choice. We could tune, and not all civilizations on Earth tune their instruments this way or tune their music this way. Like Indian raga music is not organized around this idea, but like Western classical music and ultimately therefore like blues and rock and hip hop and everything are still sort of, they're organized in this coordinate system where the center of it is this 440 hertz. What Diane is getting at in part is that that's just a choice. It's not necessarily the objective best. It's not the objective only choice that could have been made. And it's not necessarily the best choice. There are good arguments for tuning things differently. And that's what she's raising here. And I'm definitely not here to, make an argument one way or the other. It is true that historically, we're all tied around 440 as our like sort of central base frequency on the piano. But yeah, I'm sure it's totally plausible that 432 might work way better in a lot of contexts. It would take, it's just kind of like forever we were doing imperial units, feet and inches and miles. But there's really good arguments for switching over to the metric system. But it's like really hard to switch over when you've been doing something as a culture for that long. So yes, at some level, this is a cultural thing. And I don't know. Wait, is it even a piano? How come it's a joke? Yeah, I mean, so my answer to part of Diana's question when she says, how come is it generally said that music is tuned to 440, like rather than 432? It's pure history. Like we say that because it is true, because it has been true, but it doesn't necessarily, it's not necessarily that it should be true. It just is. And it's because of Bach, because Bach was Bach. I mean, if that makes any, we could change it. And it might be better to change it, but that's just the way it is now. That what we call middle A, well, the way we say a piano is in tune, if everything is in tune to its middle A and its middle C, and if its middle A is actually a frequency of 440, that's like what we're used to now in the Western world. But yeah, what I'm asking is Manuel. Now, but then her other question. It's a great question. It's a super good question. We could do a whole course on this other question. It's such a good question. I'm not sure how well I can handle it right now. She says, what I'm asking is, when multiple notes are played at the same time, how does the wave look? Yeah, okay. So that's like a whole thing. Well, and we are going to partly get into that. I kind of have to delay on this and say the underlying principle behind the answer to that question is that waves do something called interfere with each other. We have to get into this in this class. You all kind of know about this from like 7th grade or high school or something. Like, okay, I don't want to get too crazy, but I do want to say something about this. Remember, from day one of this class, and again, to everybody, it may sound like I'm just about to go off the topic onto Diana's question. That's kind of true, but kind of not. Like Diana's question is totally central to what we have to unpack in the class. The only question is whether we will be unpacking it next week or right now. So I'm going to unpack it a little bit right now because she's asking right now. Okay, so this is not a digression. It's not off the topic. It's just a little bit of a jump. And it's super interesting. And it's definitely more interesting if one of you guys asks it than if I just like talk about it. So I beg your indulgence for a minute. Let me remind you all. In fact, yeah, I'll write it down so it makes it official. Hold on. Okay. So slight sidebar here, but super important and super important for later. Remember, we're now analyzing the motion of waves rather than the motion of particles. Now we're finally there. We're sort of at the center of this course now. We're finally at sort of the whole thing that makes physics 102 so different from physics 101, so much more abstract and in a way more exciting, I think. It's still all physics. It's still all how something goes from here to there in space and time, right? Everything in physics is motion. But remember, we started off this whole class by saying that the difference between this topics and the physics 101 topics is that here we were going to be studying the motion of unthingy things, right? That's what we said. And we did a whole like weird demonstration in the first couple of days to look at the difference between thingy things and unthingy things, or what is more technically, more properly called the difference between particles and non-particles, between what you looked at in physics 101, or your first physics course was particle motion, the motion of particular entities through space and time. You looked at motions, like you looked at trajectories, you looked at, say, baseballs or planets or cars or whatever, or electrons, things that when they go from point A to point B, there actually is an identifiable, discrete, material, massive object that actually occupies all the space-time points in between A and B. We are now, when we study wave motion now, what's exciting about wave motion to me, like I never get sick of it. What's exciting about studying wave motion is that wave motion is a type of motion that obeys all of the principles and practices of physics, right? When a wave moves from here to there, it traverses space, it traverses time in a reproducible, controllable, measurable, analyzable, predictable way, right? Like you can talk about the speed of a wave as it goes from here to there. And you can say, oh, well, if the sound goes at 340 meters per second, then I guess in 2 seconds, it will travel 680 meters. And you could predict where the sound is going to be, just like you would with a baseball. And you could treat the pulses of sound just as though they were baseballs or electrons or planets or anything else. But the crazy thing is that those pulses of sound that are doing all of this quantifiable, measurable motions, they are not material or particular or distinguishable or identifiable or countable objects in any way. They are pieces of information, right? That's like already weird. That's what I'm partly trying to emphasize in this whole discussion today. And frankly, at this point, I don't even, okay, we're not going to get to the math I was going to do. I don't care. I'm going to try to address these questions sort of at least to like reinforce what's going on with sound, because I think it's like worth it. And I think your questions are great. So what I'm saying right now is when we look at wave motion, we're looking at unthingy motion. We're looking at motion that's real and scientific, but it is immaterial and non-particular. Now, remember, so that's already like sort of cool, I think, but it gets very specifically cool because remember in the first couple of weeks of class, we nailed down what we really actually meant by a particle. We actually had a rigorous definition, pretty rigorous definition of what we actually mean by a thingy thing. What we said was a particle, it like a thingy thing, something that seems concrete. Why do something seem concrete and others like sound or heat or light, they don't seem concrete? Is there like something going on there? Yes, there is. Why some things seem concrete, why some things are particular is that those things that seem concrete, tangible, palpable, massive, material, distinguishable, countable, quantizable, those things, what they are things that cannot occupy 2 points in space at one point in time, right? This is what we said, the definition ultimately of a particle was something that cannot occupy 2 points in space at one point in time, and also cannot occupy 1 point in space at one point in time while something else does as well, right? Like a particle was something that can't be in 2 places at once and also cannot co-occupy, cannot share 1 point in space and time with another such particle, right? Like particles feel tangible because they bounce off each other. They feel like you can touch them, in fact, because you can't touch them, because the minute you try to touch them, they move away because they won't share. Particles don't share spaces, right? That's what particles don't do. A particle is something that can't be in the same place at the same time as some other particle. That's not everything in the world. That's particles. Waves can and are and do be in the same place at the same time as other waves. Waves are real. Don't forget, wave motion is real scientific motion. But what's different about wave motion from particular motion, in part, is that two wave motions can literally co-occupy one point in space at one point in time. What do I mean? I think I said this at the beginning of the year, and again, I apologize. We're gonna talk about this for a minute because it's just too worth it not to. And again, we would have talked about this next week, so we're just like going out of order now. Like, remember, let's do this again. I think we did it in the first week, but just also to show that you're alive. And I know there's only 7 minutes left. So while I'm talking right now, could somebody talk at the same, could one of you like interrupt me and just start talking right now while I'm talking? Just keep talking. I'm going to keep talking. Could somebody, I know it feels rude, but could somebody start talking right now while I'm talking? Like one of you just use your voice while I'm talking and just like talk over me.
This sounds weird.
Oh, cool.
Over each other, talking.
That was beautiful. That was perfect. And I hope, do you feel like you got some sort of emotional revenge on me too for all my authority? No, that was great. Now, why don't I just have Almadia and other people do that? Here's why I want them, and maybe you remember this in the beginning, maybe not. There was a moment there where it was like fun chaos, at least as far as I'm concerned. There was a moment where at least a moment, many moments, when I was talking and Al Medina was talking, possibly other people too, like Yulia, I'm not sure. But I know at least Al Medina was talking at some moment when I was talking. Now check it, check it. If any of you, and now it might have been chaotic, it might have even been assaultive to your ears. It might have been very unpleasant. And you might not have really been able to, I did. Yeah, no, I'm pretty sure I probably did. Yeah, I'm just reviewing, I'm just looking at it. Yeah, no, I think I did. So I'm just reviewing now that we're circling back. I want to make clear what that's about. That moment when you heard Al Medina and me at the same time, you might not have, it might have been impossible to understand what she was saying. It might have been impossible to understand what I was saying. It might have been all muddy and annoying precisely because you were hearing two sounds at the same time. But think about it, but if you were, which you were, right, if you heard both, think about what that means. That's actually a really deep point. If you even for 1 minute, and you know you did, if you heard her and you heard me, that means there was a moment in time where on the moment of space, at the point of space on your eardrum, there was a sound wave entering from me and there was a sound wave entering from her. Both of those waves were at your eardrum at the same time. Like you cannot have a pebble and a stone be in the same place at the same time. We discussed this in the first week, right? You can't have two electrons be in the same, you literally cannot. Right. Okay, good. So, but now think about it in this context. Now that we've been talking about waves so much, think this is a deep thing that you literally can have two sound waves in the same place at the same time. And not only can you, but of course, if you know anything about music, now I'm trying to circle back a little bit to Diana's thing and others. If you know anything about music, you know that almost whenever you're listening to music, you're never just listening to one note, right? I mean, even if no one's playing chords, even if the piano player is only playing one note at a time, which probably not. And even if the guitar player is only playing one note at a time, which probably not, still you're hearing the guitar while you're hearing the piano, while you're hearing someone sing, you're hearing chords, right? And even there, you know whether they're right or wrong. Even if you don't do the math, even if you're not like musical, you know when they work and when they don't. There are different waves literally occupying the same place at the same time, and necessarily so. That's what makes the richness of music. Now, first of all, and of course, the same thing you can do with light, right? If you've ever worked with a theater, you can shine a yellow spotlight on the spot, and you can shine a blue spotlight on the spot, and the blue spotlight doesn't chase the yellow spotlight out of the way. Right? Like this isn't a trivial example or a technical example. It's like fundamentally true that you can have two lights in the same place at the same time, two sounds in the same place at the same time, but you can't have two baseballs in the same place at the same time. Now, to Diana's question, and again, just so that we have like some closure here or whatever, what happens when you have a wave and another wave, like one frequency and another frequency at the same place at the same time. Well, that's called interference. When two waves, when two crests occupy the same place at the same time, their amplitudes add. You may know this or remember this from 7th grade or something. And you could see it with water waves, or you could see it with wave pulses on a string. When amplitudes are moving along and come from different directions, the moment the two crests like hit each other, they don't knock each other out. They become one for a moment, which is really weird in itself. I'm going to end on this note in this point, but this is, many of you have done things with constructive interference or destructive interference. Realize what a powerful and deep idea that is. If I know a lot of you know the math, like, okay, if you have a crest of +5 hits a crest of +5, it makes a crest of 10. I mean, that's true. I'm not mocking it. It's true. Or if you have a crest of height +5 hitting a trough of -5, they'll destructively interfere and you'll get full cancellation. You'll get nothing. Okay, the math is not hard, but the concept is wild, because if you really think about what you're saying when you believe that, and you should believe it, you're saying that two crests that are coming along, hit each other, they momentarily become one big crest. In other words, they both yield and morph into one piece of information, into one big piece of information. But then a moment later, they keep going, right? They pass through each other like ghosts. A moment later, they shrink down, and so for one moment, they become this big crest of 10. And if you just look at that crest of 10, you don't know if it was made up of 2 5s or a 7 and a 3, or if it just was a crest of 10. Like, all the constituent pieces of information seem gone for a minute, and you just have a crest of 10, or you just have a note that's an A or whatever. But then the ripples keep going and they go back to whatever they originally were, as though they had a memory or something like that. Like, this is what I mean when I say information is propagating. Anytime a wave is information is somehow getting combined together, superposing together into something we call interference, but being preserved somehow invisibly, so that then it can keep going on undisturbed after that momentary like morphing of two immaterial entities. This is interference. So the ultimate answer to Diana's question, like, when you put a lot of waves together, if you put a lot of cosine graphs together, then it makes a more complicated shape. It can make, all the amplitudes will add, and you just get a new graph where all the values of all the heights on the y-axis just literally add together. So you can get things called a square wave or a sawtooth wave. Like, you can get all kinds of different shapes, but it's all temporary in the moment that the things all come together. Waves add and make more complicated waves, and the adding is called interference or superposition. And the fact that this happens is how we don't just have sounds. We don't just have noises. We have sounds, and we have music, and we have all this richness, because waves can add together and make much more complicated shapes than sine and cosine are just the basic ingredients of waves, I guess is what I'm trying to say. Waves can get very, very complicated, but what's crazy about them is no matter how complicated they get, they preserve information, specifically frequencies. The frequency is there, and then it makes it to our brain, and that's how, if you understand a word I've said all day today, if you understand one word, that's miraculous. If you heard one word, it's miraculous. Like, literally, I mean, if you recognized one word that I said, somehow that means it got from my mouth through the air. Forget the internet, I don't even understand that. And then it got to your ear. I mean, I do, but I don't. And then it went to your ear. Like, every little one note that I'm sending to you, if it got to your brain at all, it's actually amazing that happened, let alone that you might understand what I'm talking about. That's all waves. It's all waves. And it's, yes, waves add together to make more complicated waves, because two waves can be in the same place at the same time, unlike particles, which cannot. Okay, so we didn't get to what I was going to do. It's okay. What I was going to do, we'll do next time. But this is just to give you a sense. Waves are phenomenal. All right, but I do think that's the end of class. So for good or for bad. I mean, I'll hang out for a second if there's any more questions. Sorry, I didn't answer all the. Well, yeah. So goodbye. I mean, I'll hang for a second because I know I didn't really answer all the questions. But have a good weekend. Yeah. Yes, have a good week. I mean, yes. And I went, but okay, I'm gonna turn up, but I'm not going anywhere.